Hey everyone, welcome to my channel. So today we will be looking at how to drive a 7 segment display through an FPGA using Verilog. So we will be trying to display hexadecimal digits on a single 7 segment display of an FPGA. We won't be demonstrating on an FPGA though. We will be writing a Verilog code and try to synthesize it and show the netlist on EDA Playground. But before that, first we will like to look at what exactly is 7 segment and how it works, right? So basically a 7 segment, as its name suggests, there are 7 segments of LED in a display arranged in a manner like this. So this will be this will be a typical 7 segment display you will be seeing. So there are 7 segments. You can name it as A, B, C, D, E, F and G, and one dot which is called DP. So this is used for representing floating point numbers for a division. Like it will be a type of a divider, you can say, but so visual divider. So and this is a 7 segment. So now we all know an LED consists of an anode and a cathode, right? And if you supply a positive voltage and you supply a positive and negative voltage correctly, a current passes through it and the LED glows. If a separate opposite polarity is applied, then the LED won't glow. It's a simple diode mechanism, right? So now, what do we do in 7 segments? Now, since there are 7 segments of an LED, so we will have 7 cathodes and 7 anodes, right? So what we do in 7 segment, what's special is we make one of these as common. Either cathode will be a common or anode will be a common, right? So this brings us to two types of 7 segment displays. One is called a common anode and one is called a common cathode, right? In common anode, all the anodes are common, and in common cathode all the cathodes are common. So if I can make you visually show you, so the 7 segment this is our 7th segment. We have 10 pins on this segment here. If I can just show you an uppercut display of it. It's seen like this, and if I can just draw the segments, just give me a moment, right, and a dot. Okay, so the center 2 pins, this and this is our common pin. This is the common pin, and we have A, B, C, D, E, F, G and DP connected to all of these wirings. Now I currently don't remember the exact connections. You can look at it on the Google for these connections, but typically it looks like this only, and this common 2 pins are actually internally shorted, right? They will all be internally shorted, so you have to supply supply a potential to one of these segments one of these pins only. You don't need to supply on both of these. So in case of a common anode, you will have to supply plus 5 volts or plus 3.3, whatever. You will have to supply a positive voltage here, and for common cathode type, you will have to supply ground to it on common cathode. I'll write a short forms for this. Common anode. Now after supplying voltage to this common pin, on the only thing which we have to do is uh, control all of these 7 segments to glow the LED of these. So if you want to glow LED of A, you will have to supply ground in case of common anode, or plus 5 volts in case of common cathode. Similarly for B, C, D, E, F, G and the dot, right? So this controlling has to be controlled through a code, Verilog, through a circuit, which we will be writing in Verilog, right? So now first we'll have to see what we have to display on these 7 segments, and how in terms of A, B, C, D, E, F, G and D, P, how we can make them glow through a code, right? So okay, so if we want to display a 0 on a segment, so I will draw the segment once again, and if I can make a chart here where I'll keep DP on the MSB side and A on the LSB side, A, B, C, D, E, F, G and DP, right? So this is this R7 segment display. Okay, now if you want to drive a 0 here, I'll be driving DP to ground for this moment, because we have to drive a single digit only, so we'll be driving DP to ground. Now for 0, I'm just showing you in green. We need to if we glow these LEDs which are in green, then you will be able to see, you will be visualizing that A, B, C, D, E, F and G. Now only A, B, C, D, E and F needs to be glown. So we can write a code for this, 1 for representing glowing the LED, 0 for not glowing the LED. So G will be 0 and A, B, C, D, E and F becomes 1. Similarly for 1, if I can just show you, we only need to glow B and C, right? So we will only be marking B and C as 1, rest everyone becomes 0, right? Similarly for 2, we need to glow it in this fashion. If you can imagine the green path here, so this becomes 2. So A, B, D, E and G needs to be glown in this case. So we will be writing A as 1, B as 1, D as 1, E as 1 and G as 1. So rest everything will be filling as 0. So like this we can imagine each of these all of these digits, like 3, 4, 5, 6, 7, 8, and we can fill up this table here. So I won't be going much deeper into it. I'll just fill this table and show it to you. So as you can see, I filled up the table here. So I'll only I've explained 0, 1 and 2, so you can just manually try to do it on paper and see how this 3, 4 and 5 have been decoded out. So this is the table which I've written. As you can see, this is you can treat these as an 8-bit binary number, right? So now since we need 8 pins to drive this, so we can determine that we need 8 outputs to drive this LED segment, right? So now on these 8 pins we can directly drive these values based on which number which we want to display on the 7th segment, right? So this much we have came to know how many pins we will be requiring to drive the segment, and what values should be driven for each of the segments to be glown in the particular fashion. Like for 0, which values will be supplied to these pins, so that 0 can be displayed on the cathode, on the 7th segment, sorry. So as you can see here, the code is actually I have written 1 for correspondence of the glowing of that LED, right? So in case of a common cathode, we know that the common pin is tied to ground, right? So now we will have to drive A, B, C, D, 1 to glow and 0 to not glow, right? So for all these segments we need A, B, C, D, E, F. All of these segments need to be supplied to 1 so that all of these can glow, correct? So as you can see in this code, it's representing the same thing. So now if you want to drive a common anode display, in common anode, common pin is actually tied to a positive voltage, positive supply, right? So now for driving A, B, all of these segments, we need to supply 0 to them, or you need to tie to ground to glow them, correct? So in the code, if we are able to negate this value, the 0, if we are able to negate it, if we can put a NOT gate on the values being driven, so we can drive a common anode and common cathode both. So we need one extra input we will be requiring, which will tell us whether the display is common anode or common cathode, right? Okay, so we have determined that one input is required for telling whether it's anode or cathode. 8 outputs we require to drive the segment. Now what we need to drive, that we will be requiring it as an input, right? Since we are driving a decimal digit 0, 1, 2, 3 to 9 till 9, so 9 can be represented in 4 bits, right? So 4-bit input will be required. 4-bit input is enough to tell whether a number is 1, 0, 1, 2 or 3 or till 9. So 4-bit input to represent number to be displayed. Correct. So now we have come up with all of the inputs and outputs which we require in our code, right? So if I can write the module definition, so let's write what we do is we write module, then we give the name of the module. So here we are driving decimal digit to 7 segment. We can give a name like this, and then we can write all of the inputs and outputs which are required. So right now we require an input which is 3 down to 0, which will be our digit, right? Then we require an input which will tell us common anode or common cathode. So we can write it as I have written common anode or common cathode in the short form. And now we will be requiring output. 8 outputs are required. So there are 2 ways in which we can do this. One is we can have separate wires like output A, output B, output C, right, like that. Or we can make it as a 8 bit vector 7 down to 0, and we name it as A, B, C, D, E, F, G, D, P. We can name it like this, a combined name we can give. And now we know this vector will be this 8-bit wire is our output, and this 8 bits will be connected to the 7 segment display in this fashion, and we will be able to display the number accordingly, right? So we require this much input for now, and we have to put in semicolon. So we know this is the module. Now how we will be driving this, since there are 8 codes now, there are 10 codes actually to drive each of these 7 segments. So what we will be doing is we will be writing a case statement depending on the digit, and we will be driving it accordingly, right? So let's first drive it using a case statement. So we how we write it, so always @digit. So whenever digit will change, we have to trigger this block, right? So now we do a begin, and we do a case, we write a case digit, right? And we we don't need to have a begin and end in terms of case, because case and end case are enough. But in Verilog of 1995, it was required to give a begin end after case also, but now it's not required. So now we know we have digits. We have digits from 0 to 9, right? Since digit is a 4-bit number, it can 4-bit number can go from 0 to F, right? But we this is a double slash represent the comment, so 4-bit number can represent to 0 to F, but we require to drive from 0 to 9, right? So now we'll be looking at how to tackle all other cases in that case. So let's get into it. So we know 4 take D, since we know it's a 4-bit number, so we have written 4 take D0, and we give a semicolon. Since we have to write only one statement, you don't need to give a begin end in this case. So what we can do is directly write since the output since the output is a wire and we are in an always block, so we cannot drive an output directly, right? So what we need is we need a reg variable declared in our code, which we will be assigning to the output through assign statement after this always block. So we will be taking a 7 down to 0 reg, and it will be a temp. You can name another temp value, right? So now let's go into the code. For 4 take D0, we write temp equals to whatever number we have taken, so 0 0 1 1 1 1 1 1. So we know we write 8 take B 0 0 1 1 1 1 1 1, right? Similarly 4 take D1, temp equals to 8 take B 0 0 0 0 0 1 1 0. 0 0 0 0 0 1 1 0, right? 4 take D2, temp equals, so this is a separator here, this name 8 take B. Now 2 is represented as 0 1 0 1 1 0 1 1, so we are writing at 0 1 0 1 1 0 1 1, right? Similarly we can write for 4 take D3, 4 take D4, D5, and so on. I'll fill it afterwards, but since we have to just copy the values from above only, so I'll not waste much time in this. Now, after covering all of these 9 digits, right? Now, what happens if someone in the input gives all ones to it, or F, as I can say on the digit side, if I supply all ones, or suppose somebody supplies anything else. So what will be our go-to strategy in that case? What should be our go-to strategy? So case actually provides a default value where you can give what is to be done if none of our cases are getting satisfied, right? So that can be given in default statement, right? So by default, since it's not satisfying any of our cases from 0 to 9, so we need our not to glow the display. So what we can do is we can supply 0, all zeros to it, correct? So if you give anything other than 9, your code nothing will be supplied to the segments, and segments will not glow, right? So this is our this will be our case statement, and now since after case we give an end case here, so we give an end case, and we after begin we give an end here, right? Now, as I told you before also, we will be trying to drive both the types of the 7 segments, whether it is common anode or common cathode, and we took an input specially for it, CAOCC. So this will be telling us common anode or common cathode, right? Now I'll assume that if somebody supplies 0, CAOCC, by default, since we have written all of our digits according to common cathode, so if this is 0, then in that case this will represent a common cathode. And if I give CAOCC equals to 1, this will mean that we need a common anode. It's a common anode type, right? Now, how to tackle this situation on the output? What we will be doing is, as I told you, we have to use an assign statement on the output A, B, C, D, E, F, G, D, P, right? This was our output. We will be writing a ternary statement here, and ternary statement what it does is we say here CAOCC equals to 1 take B1. So we are comparing CAOCC with 1, right? Now if this is 1, question mark. Now if this is 1, the first part of this code will be executed, otherwise this second part of this code will be executed, right? So now what we have to do is, if CAOCC is 1, in that case we know that it's a common anode, and I have told you before also in the video that for common anode we can negate the values of the this binary value. So if we negate the temp value here and we give the supplied and we supply that to the output, we will be achieving our goal of driving a common anode display through a common cathode value, right? So if this is 1, then in that case I will supply not of temp, so I have used a unary operator here, so this will just negate all of these. Otherwise, if this condition is false, it will assign temp directly to the output. Simple. This is the simple code here, and now since we have finished our code, so we'll be writing end module in the end. So this is a very simple code which I have written, which I have shown you. I have just shown you the concept. I will be showing you how the code will be written in full code will be written in Verilog, or I have almost written it, but how it gets compiled and how we'll write a test bench for it to see how the values gets displayed on the waveform. And we'll try to synthesize it also on EDA Playground through Mentor. I think Mentor Precision is there on EDA Playground, through which we can synthesize this, and we will be seeing what circuit actually it's making, right? So that's all in the video for today. Thank you for seeing visiting the video. Please do subscribe to our channel for more of these videos. Thank you.